everyone who missed the first slide, but we'll keep going. So this is a way of having naturally many atoms or ions that sort of talk to each other in a collective fashion. It gives efficient global connectivity. What's less obvious is to what extent is this programmable, and that's something that we've been exploring in my group. And so in particular, I'll talk about kind of a set of experiments exploring using global cavity-mediated interactions combined with local control to program the spatial structure of entanglement among atomic ensembles, or to program the graph of interactions as a kind of toolbox for quantum simulation. And I'll talk about applications in two directions. How can this programmable entanglement be used for multi-parameter sensing tasks with an enhancement from entanglement? And in this space of quantum simulation, I'll talk about using these programmable cavity-mediated interactions as to kind of expand our toolbox for probing topological physics. And then I'll also along the way give a bit of an outlook to saying these are experiments that work with atomic ensembles that talk to each other via light, but what are the prospects for pushing this into a regime of single atom qubits with sufficiently strong atom-light coupling to explore coherent interactions. And so that's kind of the outline of my talk. And I'll just mention sort of, I would say there are sort of two toolboxes that are coming together in what I'll talk about today. So one that's quite well established is the use of a single cavity mode to generate collective entangled states by the sort of massively parallel entanglement that's possible by coupling many atoms to a single cavity mode. And Mark and James are experts in sort of generating entangled states of hundreds of thousands of atoms in this manner. And then on the flip side, there's been progress in a number of groups over the past few years in kind of combining this toolbox with the techniques of local control and detection. And I think we'll hear, for example, we've already heard some talks about that. We'll hear more about that from Dan Stamper-Kern, for example, tomorrow. And so kind of putting these two ingredients together is our approach to having these programmable non-local interactions. So just sort of, right, the basic building block is that two atoms, let's say I have two spin half atoms, they can, in principle, exchange a photon that lets them exchange their spin states via a cavity. And when one scales that up to n atoms and it's a single mode cavity, this naturally gives you some all-to-all connectivity. And the new kind of tools that we've been adding to this in my group are the ability to program this graph of interactions by adding in optical control, to probe the spatial structure of entanglement by imaging the correlations in the system. And also the cavity gives a way of actually kind of directly accessing non-local quantities. And I'll talk about this interaction-based readout of non-local quantities as a tool, both in quantum metrology and in quantum simulation. So this is our cavity that when we built it, it seemed pretty crazy, but it's not so crazy compared to a lot of the things I've heard about this week. It's a near concentric cavity that has a waist that can be anywhere down to about 12 microns. The experiments I'll talk about, it's an 18 micron waist, and a moderate finesse that gives a single atom cooperativity that's larger than one, but not way larger than one. So it looks something like that. Maybe the craziest thing about it is that it's set up on 5-axis tip-tilt stages, which allows you to fine-tune the distance from concentricity and fine-tune the tip and tilt to maintain this near concentric alignment. Perhaps overkill, but that was what we did when we built this. Inside of this cavity, we essentially trap an array of atom clouds. And so this is sort of, we've heard about some cavities with very tiny wastes, and that's great for having a single atom. But if you actually want to have many and have, let's say, a millimeter long region that's reasonably strongly coupled, this is actually a nice regime to be in a long cavity with a sort of 10 to 20 micron waist. And so in that region, that strongly coupled region, we can have up to about 20 clouds of atoms. Each of them has about 1,000 rubidium atoms. And just for sort of giving the full picture here, you should imagine there's a 1560 nanometer lattice that's commensurate with the 780 nanometer lattice that actually couples to these rubidium atoms. And so the atoms can either be trapped in this intracavity lattice, where you directly align them to the light that mediates the interactions, or via some micro traps that are incident from the side. And it turns out that sort of hybrid configuration allows us to arrange the atoms in these clumps. We cool them in the micro traps, and then we do our physics in this intracavity lattice. Okay, and then, so we have kind of basically two tools. If we want to let the atoms talk to each other, we turn on a drive laser that mediates some all-to-all interactions. And if we want to have some control of the structure of interactions, then we also can drive spin rotations via light shifts or Raman couplings from the side, via beams that are incident from the side. So that gives us spatial control. So here's like a typical picture of what some experiment in this setup might look like. In this example, there's an array of 14 clouds of atoms, although we're not in this setup looking at the dynamics of individual ones. We're kind of grouping them in some super sites that we address, and we look at sort of how they exchange their spins between these sites. So what's actually going on here? So you see some oscillations in the difference in spin polarization between this left group and the right group. So this is for some spins that are mostly initialized down, except the ones in the right are tilted to be along the x direction. So what's going on here actually? Why are the left and the right ones talking to each other? So what we've actually done here, in general, what we have is this global kind of spin exchange coupling. And then we also have the ability to apply some local fields, which could turn the spin exchange on or off resonant between given regions of the cavity. And incidentally, this general form of Hamiltonian is one that I think you might hear about in James's talk as for simulating the BCS model. Jean-Philippe has been looking at this type of model for looking at random spin models. This will be or the sort of workhorse also for my talk. And okay, so why is it that the left and the right regions are talking to each other in this way? One way you could imagine doing this is, say, I want spin exchange to be resonant between these two subsets of my array, but not for the middle. So that's one way you could imagine getting these dynamics. Actually, the full story that's going on in this particular data set I'm showing is we have, different light shifts on different regions of the array from these local addressing beams from the side. And when we want to turn on interactions, let's say between, in this case, the left and the right subsets, sub-arrays, we modulate our drive field at a frequency that's resonant with the energy difference, the difference in Zeeman energies for the left and the right sites. And so basically, by having some pattern of light shifts that's spatially varying, and by choosing the frequency at which we modulate our drive field, we can sort of resonantly couple, in principle, any pair of sites. But this is just sort of one example. You'll see later in the talk a bit more of the context for this particular measurement. So that's some illustration of kind of the mean field dynamics that you get from this cavity-mediated spin exchange. Now you might ask, or should I just think of each of these regions as some big classical spin, and they're rotating around each other, and these dynamics you can pretty much understand in that picture. But it would be nice to see whether there's actually something quantum mechanical going on. And one way that we like to sort of probe dynamics driven by quantum fluctuations in this system is actually leveraging the spin 1 internal structure of these rubidium atoms. So let's say we start with all of the atoms in the m=0 state, and we turn on the light in the cavity. That actually drives a process where there's no net magnetization, but 2 0 atoms can turn into a pair of atoms in the +1 and -1 states. And that looks like it should be one mechanism for generating entanglement. And indeed, it's been studied, well studied, the collisional version of this in Bose-Einstein condensates. There's been work in Tillman's group looking at a variant of this where spin and momentum become correlated through interactions in a cavity. So we like looking at the spin 1 system as one way of probing sort of dynamics driven by quantum fluctuations. Here's an early experiment where we had an array of about 20 sites, and you can kind of look as a function of different shots of the experiment at the populations in the 3 states. And one sees large fluctuations and are the atoms in +1, -1, or 0, but they're always kind of correlated between +1 and -1. And they're also spatially correlated across the array because so far we're just looking at these global interactions. Now, if you want to say more than that these fluctuations look correlated, but actually say something about entanglement, then it's useful to look at the quantum fluctuations in more than one basis. And in particular, for this spin 1 system, there's sort of a generalized block sphere within which one can see some squeezing of quantum fluctuations. So the coordinates here, the initial state, there's some spin and quadrupole moments, which are like the sum of the individual spins or quadrupole moments of the individual atoms that lets us to define these collective variables. And what will be important is basically, if when we start with all atoms in the 0 state, you can think of that as a coherent state along this axis that I called QZZ. And when we turn on the cavity-mediated spin exchange interactions, that generates a nonlinear term, an fx squared term, that where the lowest order effect is to squeeze these quantum fluctuations. And so we can actually then, just by measuring, in this case, it's an array of 4 atom clouds, but so far we're just looking at collective observables. It doesn't, the spatial positions don't matter. And we can see that the quantum fluctuations drop below the standard quantum limit that tells us that this is an entangled state. It doesn't yet tell us anything about the spatial structure of entanglement. And we said we wanted to start to have some control over that. And just to say, why might you want to control it? Some of the applications of atoms as quantum clocks or sensors have to do with, let's say, can I study fundamental physics of gravitational redshifts by having arrays of clocks? If you can entangle them, you can get to higher precision faster. Ben has done work using atoms to probe magnetic fields. If you want to image the field with enhanced sensitivity, maybe you want some control over the spatial structure of entanglement in your system. So how do we control the spatial structure of entanglement? And just to give a flavor, there's various things you might want to do. If all you're trying to sense is a global quantity, then actually this global squeezing operation is great. But if you want sensitivity to gradients, you might want the ability to say, rotate a state that is sensitive to a global field. By doing local rotations, one can convert that into a state that's sensitive to a gradient. Maybe you want independent squeezing in different ensembles, or maybe you want some fancier control of the graph of entanglement. And a minimal instance of that actually is having EPR type entanglement, where you maximize the correlations between 2 ensembles. And that already is actually an interesting resource for some sort of counterintuitive sensing tasks that I'll get to. But broadly speaking, so I'll say, like, if I want to have some particular structure of entanglement, a nice sort of class of states to think about are the so-called graph states, which you can think of, they're well sort of studied in the case of qubits as the state you would get if you have some graph and you have a controlled Z gate on each edge. And these are known as resources for universal computational resources, where if you make the state, subsequently you can do any computation just by measurement. But there's also a version of this that's studied primarily in photonic systems, where the degrees of freedom aren't qubits, but they're some sort of bosonic continuous variable system. And it turns out these large spins made by ensembles of atoms, we can pretty much describe them by sort of the fluctuations, right, in 2 quadratures about the collective spin. And so I'm just going to call those quadratures X and P. I'll forget the names I gave them before, and just say there's a class of states we can think about engineering, which are described by essentially what is the graph of correlations between these kind of effective oscillators that I'm so mapping these large spins to. So the idea would be, in principle, if I had some Hamiltonian that looks like xi, xj on some programmable graph, I can make, if I can choose the structure of the couplings, I can kind of make any graph of entanglement. But in practice, what I have access to is actually global interactions via a cavity, and it's not necessarily obvious how I would, specify this graph. But it turns out that actually these collective operations are already quite powerful. If you think about it, if you give me a graph that says here's the structure of correlations I want, what I can do is I can write that as a matrix. I can diagonalize that matrix, and that will actually give me a set of collective modes that are the right basis sort of in which to think about this entangled state if I want to make it with a cavity. So as a minimal example, if I want an EPR type entangled state, which is 2 nodes where the entanglement is maximal between them, I can actually diagonalize this graph that specifies the structure of entanglement, diagonalize that matrix, and it'll tell me the modes I should squeeze are the symmetric and the anti-symmetric modes, okay? You can diagonalize that in your head. So it says I should squeeze basically, and in particular, the eigenvectors will tell me which modes I should squeeze. The eigenvalues will tell me which way I should orient these, the squeezed quadratures for the 2 modes. So in this case, the eigenvalues are plus or minus 1, and that tells me I should orient these 2 squeeze states in opposite directions. And that's a prescription that naturally maps onto the control knobs that I have in my cavity. I can apply a global squeezing operation. I can do a pi pulse on half of my system to convert the symmetric mode to the anti-symmetric mode. I can do any phase space rotation to pick out which is the squeezed quadrature. And then I can do one more global squeezing operation, and now I have this prescription for the EPR type entangled state. And indeed, if I measure kind of the quantum fluctuations, I can see they dip below the standard quantum limit in the symmetric mode shown here in red, and then the anti-symmetric mode shown in blue, in quadratures that are 90 degrees out of phase. And one can map that back to saying what's also the spatial structure of correlations, and you've sort of maximized correlations between the ensembles, while actually undoing the correlations within the individual ensembles. So that's kind of just one example of using cavity plus local control to build a minimal sort of graph of entanglement, which already is actually interesting because there's some form of squeezing in two non-commuting variables. And this actually can be a resource for simultaneously sensing perturbations in two different quadratures, which might seem a bit counterintuitive, and I'll come back to that in a moment. But just to say a bit more, this approach you can scale to fancier graphs. The fanciest thing where we kind of provably generate entanglement is this square graph, which one can build by, again, diagonalizing this desired correlation matrix, tells you these are the modes that I should couple to the cavity. And so by sequentially squeezing, flipping spins, squeezing, flipping spins, there are sort of 4 operations that produce the correct structure of correlations. And that is this 4-mode square graph state. So that's kind of illustrating a general way of building a given graph of entanglement, not by pairwise interactions, but by global cavity-mediated interactions. One thing you might ask is kind of, okay, so far the squeezing here is kind of just at the level of a factor of 2. Can one do better? And it turns out one nice way, one thing that's actually limiting us in the measurement I showed before is just our ability to detect the squeezing. So it turns out if what's limiting you is your ability to detect this very small quantum noise, it can be helpful to amplify it back up before you measure it. And the cavity, it can squeeze quantum fluctuations, it can also amplify them. So we can do sort of a squeezing operation, then apply some perturbation that we want to sense, that's this arrow in green. And if we want to sense it better than in the previous example, what we can do is before we detect, we switch the squeezed and anti-squeezed quadratures, and we apply the cavity-mediated interactions again to amplify the quadrature that the signal is in, and then we measure. And that allows us to crank up our metrological gain to a factor of about 5 beyond the standard quantum limit, the 7 dB. And the fun thing is that you can do this for if you want to be sensing a global field, then this is the protocol, but you can also give yourself, for example, sensitivity to a field that couples to a different spatial mode. So if my field is oscillating and I want enhanced sensitivity for this oscillating field, then after I do my squeezing, I can map this, this squeezing onto the spatially oscillating mode. I call this the k equals pi mode, right, where there's a pi phase between adjacent sites. And then before I do my unsqueezing, I'll also do some local spin rotations that map this mode I want to sense with to the mode that couples to the cavity. And in this way, I can also get sensitivity to a displacement that's spatially varying. And one could generalize this actually to any spatial mode. Okay, so there's a few different directions this can go. It's natural to now say, well, I can map my entanglement to any spatial mode. And if I want to do some image classification task, for example, maybe I actually want to figure out what is the optimal set of spatial modes to squeeze for that task. And so there's a whole direction there of asking how one can prepare sort of optimal states for tasks that are involve sort of multi-parameter sensing, sensing with spatial resolution, or sensing spatial correlations. One might also want sensitivity to not just a scalar, but say a vector quantity. And that gets into this fact that actually this EPR form of entanglement can give you sensitivity to more than one quadrature at the same time, to changes in more than one quadrature at the same time. And so that actually could be a resource, let's say, for vector magnetometry. And interestingly, there's been recent theoretical work saying if you can actually have simultaneously sensitivity to displacements in what I called X and P. So, for example, in two non-commuting observables, spin observables, there are certain tasks where you can actually get exponential speedups if your problem involves, for example, characterizing some spatiotemporally correlated noise. So that's a sort of exciting. direction, and it requires using that EPR type entanglement that we can make. But it's not enough to make that type of entangled state. One also has to be able to detect it. So what do I mean by that? So here's an example of a task that might benefit from this EPR type entanglement. Let's say I want to simultaneously image orthogonal components of a magnetic field. And I said image because you sort of, usually a quantum enhancement will come about when there's some external constraint. So here the constraint would be I want some spatial resolution. There's some fixed number of atoms I can fit into each pixel. And then there'll be some limit on the uncertainty product of my sensitivities to these two field components, which will go as 1 over the number of atoms I can fit into a pixel. And you can't, and you can squeeze and win in one quadrature, but you can't win in both at the same time. If you want to maybe win in both quadratures, you could try to do something fancier, which is say I'm going to take my sensor and entangle it with some reference system. So these could be some spins that they could be far away. They can be in magnetic field insensitive states, so they don't couple to the quantity, the field that you're trying to measure. And now what you would want to do is take advantage of the fact that for this entangled state, I simultaneously have squeezing in the sum of the x quadratures, so x might be fx for my collective spin, and the difference of the p quadratures. And so if my field only couples to subsystem A, then I can actually measure XA and PA to arbitrary precision if I have arbitrarily strong squeezing in this EPR type state. So the sort of basic thing that allows this is the fact that the sum of the x's and the difference in the p's commute. There's no uncertainty relation that constrains how well I can measure both of these. Just because there is no uncertainty relation doesn't actually mean I have a good way of measuring both, right? So, so like, how do you actually measure these non-local observables without getting the local information? So that's important to be able to use this, this trick. So actually, Eric, who's in the audience, pointed out that, hey, one way we can actually do this is use the cavity to amplify the signal in these two non-local observables. So use that cavity-based readout where the cavity not only squeezes, but can amplify a signal. So the basic protocol is we prepare this EPR state as before. Then we have some displacement of unknown, in some unknown direction in phase space. And what we'll do in order to measure it is we'll amplify the symmetric mode in the x quadrature and the anti-symmetric mode in the p quadrature. So this is, again, two pulses of sort of cavity-mediated interaction that amplify first the symmetric and then the anti-symmetric mode. And now we have a big signal in the two quantities that we care to measure, and we can just read out actually in this 45-degree quadrature. And we can read out just by our standard imaging in a basis that has information about both x and p. And essentially, the information in the symmetric mode will tell us about the kind of real part of this complex alpha, that's our displacement in phase space. The anti-symmetric mode will give us the imaginary part. And so we can then get sensitivity without a priori knowledge of the phase to better than this green circle is the local Heisenberg uncertainty limit. What is the best you could do without entanglement with that reference region? So far, this is two subsystems of our array. And in principle, one could also ask about scaling this up to multiple entangled states. And that's where one could get sort of the largest enhancement for some of these sampling tasks where one actually expects to be able to get exponential wins from the EPR type entanglement. Okay, so I mentioned this toolbox of programmable entanglement and some applications to doing sort of quantum sensing tasks that go beyond a single variable or a single spatial mode. And now it's just worth mentioning this sort of approach of generating non-local graph states with programmable graphs might also have some broader applications. These graph states can be starting points for preparing states of interest for error correction, topological states. We are doing some theory on preparing states with entanglement structure that resembles a quantum critical ground state that has some connections to quantum gravity. But some of these directions would be most interesting, particularly this first bullet point of error correction and topological physics, if you can generalize beyond these Gaussian states to, for example, arrays of qubits at stronger atom-photon coupling. So, what are some paths to getting there? So we've heard in many talks about this figure of merit, that's the cooperativity. And there's a range of different approaches to trying to get strong coupling, stronger coupling. I apologize if I didn't put somebody's latest cooperativity number on this slide, but roughly these various types of optical cavities, the cooperativity, if you work very hard and are very clever, can get up to sort of hundreds. But getting beyond that has been a challenge. And just as a sort of comparison point, if you look at, for example, superconducting circuits, right, these artificial atoms, what are the cooperativities there? They can be sort of order 10 to the 8 is standard, right? So wouldn't it be great to get into that regime? The closest thing that's been done in atomic systems is actually using similar superconducting cavity technology, right? So these, there have been beautiful experiments by Sarah Charoche with Rydberg atoms that pass through a cavity with a frequency in the 50 gigahertz range. It's a superconducting Fabry-Perot cavity. And that type of experiment, the cooperativity is in fact on the order of 10 to the 8. So there's somehow orders of magnitude difference between what can be done in this regime of microwave to millimeter wave compared to the optical. And so this is a direction that we also would love to explore in our group. And so there's kind of, I would say, 2 directions we're going in terms of next generation experiments that aim at strong coupling for single atoms. On the one hand, our optical cavity is not yet at its limits. And if you want to hear about how we aim in a similar near concentric cavity to work at a cooperativity in the hundreds, Raj has a poster on that. But also we've tested out a superconducting millimeter wave cavity that has a measured finesse of about 60 million that corresponds to a cooperativity up to a few million, and that has the optical access required for trapping single atoms inside. And Tony Zhang and Sam Cohen have a poster on this cavity. We're still waiting on the cryostat that will let us trap atoms inside, but that's, I would say, an exciting potential direction for having sort of an orders of magnitude different regime in terms of the strength of coupling of single atoms to photons that may allow for translating some of the ideas I talked about in, let's say, preparing arbitrary graph states via these cavity-mediated interactions also to single atom qubits. Okay, so I talked about sensing as one direction for the atomic ensembles in the optical cavity. And then I said that this programmability could also be a resource for some new directions in quantum simulation. And in particular, a common theme that I want to emphasize is we talked about how the cavity lets us control and also directly detect non-local degrees of freedom, right? That was useful for this story of using an EPR entangled state for sensing. And that could also be useful in the context of simulations of topological physics, where the whole sort of kind of neat feature is that it's possible to encode information in some non-local degrees of freedom. Can a cavity help you access them? So sort of motivated by that, I want to say a little bit more about, first of all, using the cavity to kind of generate a programmable structure of interactions that might let you access some topological physics, and then asking how does this non-local readout help? So let me take a step back and say, okay, so I showed how you can sort of controllably build up a given desired graph of entanglement. We could also think more in the spirit of quantum simulation. I might want to just simulate a Hamiltonian with some non-trivial coupling graph. And the general picture I gave before in sort of building up these entangled graph states is that the cavity naturally couples to collective degrees of freedom. So we should think about like what is a natural set of collective modes to give the structure of entanglement or the structure of interactions that we want. So as an example, if you want to build a translation invariant graph, and it could be, translation invariant, but with some exotic long-range couplings, the natural basis of modes are actually spin waves. So it's natural to actually engineer translation invariant graphs by coupling the cavity to a set of different spin waves. And one way that one can sort of cycle through those different spin waves, you don't even need local optical control. One way to do it that we've used in the past is just applying a magnetic field gradient. So what is the k = 0 mode at a given time turns into k = a linear function of time. And so one way to now think about this system is at each time, the cavity couples to a different spin wave mode. And so by modulating the drive field in time, we can control the strength of coupling to each spin wave, or equivalently, actually, the dispersion relation of the spin wave modes in our cavity. So this E of K in this Hamiltonian that I've written now in momentum space is just directly going to be given by the intensity of the drive field as a function of time. That's sort of a collective mode picture. But we can also go back to a perhaps even more intuitive real space picture, which is to say, if I, in the presence of a gradient like this across my atomic system, the gradient will suppress spin exchange interactions. They will be off resonant, but I can resonantly turn them on by modulating the drive field at a given frequency. And so if I want to turn on, let's say, interactions at a particular distance in my cloud, I should modulate the drive at the frequency that makes that coupling resonant, so a frequency proportional to the gradient times the distance. So here's some example where modulating at sort of a particular frequency allows me to have a correlation spread not between nearest neighbors, but from to third and sixth and ninth neighbors in my chain. And that general approach now allows you, if you turn on multiple frequencies, to turn on couplings at multiple distances. And so this was an experiment we did some time ago, sort of building a range of different sort of coupling graphs that we could program in just by saying what are the frequencies present in my drive field. And now, again, that can go in a few different directions. But the one I want to say a little bit more about today is actually how can you use these programmable graphs and the ability of the cavity to access non-local degrees of freedom as a new toolbox for exploring topological physics. So just to motivate that a little bit more, there's this notion that if you have a topological phase of matter, it can give you some way of robustly encoding information in non-local degrees of freedom. And then perhaps there's some tension with the fact that you've intentionally stored your information non-locally, but that makes it hard to manipulate and access. And there's this inspiring, I think, paper that came out already way back in 2008 saying, well, maybe you could somehow couple a cavity modes to these non-local degrees of freedom, map the non-local observable onto something that you can non-destructively measure to manipulate this non-locally encoded information. Okay, so we're not yet doing this full story, but we wanted to explore this idea. And so the starting point you might want is a way of engineering a topological state in the cavity. And there's a few different routes you might go, but the route that I'll take is using this programmable graph of interactions that we achieve by this kind of modulated drive field plus spatial control. So the basic idea is that we'll be able to realize a class of models where we have some hopping of spin excitations, right? This F plus F minus is, I can map this, I can think of these roughly as some weakly interacting bosonic particles, my spin excitations. They have some hopping that I'll specify. And then there'll also generically be also some interaction on a given site between the spin excitations, because this F plus F minus, I could turn it on at a given distance, but I could also turn it on within a given site. And so a few different sort of knobs we have. We can control the magnitude and phase of the hopping, in principle, including long-range couplings, although I won't use that today. We can decide whether we have periodic or open boundary conditions, because if we want, we can, via the cavity, connect the ends of the chain. We'll have the ability to actually tune this on-site interaction, which is of interest for being able to explore both kind of simple to understand non-interacting regimes and ask what is the effect of interactions. And then we'll actually use this sort of non-local detection that I touched on as something the cavity helps with. So we decided to start with kind of the simplest model of topological physics you could imagine, which is the so-called Su-Schrieffer-Heeger model. It's just a dimerized spin chain with sort of unequal couplings between the even and odd legs of the chain. And it has the sort of a key feature of this model is that if you look at sort of the relative phase on one of these dimers, so the phase of the B site relative to the phase of the A site, one can ask, how does that phase wind, or does it wind as a function of momentum? So these are the different spin wave modes in this chain. And as one ramps the sort of changes the relative coupling strength, what I call J and J prime in this dimer, the phase may either not wind or wind by 2 pi, as a function of momentum in this system. And so that signifies a topological phase transition as a function of this ratio of the J prime to the J coupling. And another sort of signature of this transition is that there are topological edge states. So there are essentially two modes localized at the two ends of the chain, if I do this with open boundary conditions, that are well separated from the kind of bulk spectrum. Okay, so these are actually, if you want to know more about these measurements of this topological invariant, that's this phase winding, you can look at my student's poster. But I want to say a little bit more about these edge modes, right? So there's somehow two modes that are superpositions of excitation on the left and right site that are a signature of this topological phase. And so far, everything I've sort of described assumes a non-interacting system. So this is just a single particle band structure. Now, actually, it turns out even just making the system non-interacting is sort of non-trivial in our experiment. So what do I mean by that? In general, you might have, we can turn on these spin exchange couplings between sites, but there's also some interaction on the site, which we have to be very careful to zero if we want to study the non-interacting physics. So what an experiment like this actually looks like, we have some red detuned drive fields, some blue detuned drive fields, and we can play a trick where basically the red and blue detuned drive fields should generate essentially the opposite sign of interaction. But by additionally controlling the phases of the couplings, we can make it so the on-site interaction cancels, but the couplings between the sites actually add when we switch between red and blue detuning. And so then it turns out you can send in some waveform where you're modulating the drive fields, both the red and the blue detuned ones. You're both switching sort of the sign of the detuning and have some crazy waveform that allows you to specify the couplings in my chain and also dictate is the on-site interaction on or off or tune it. Okay, and actually in the experiment I showed before, we're driving with this crazy waveform and we're also adiabatically ramping its amplitude to ramp, let's say, from the nearest neighbor chain with no dimerization to some dimerized system. That's the one where we measure this topological invariant. Okay, so that's kind of, we have this toolbox. We can turn on any couplings we want. We can tune the on-site interaction. And now, I said in the non-interacting system, one signature of the topological phase is these edge modes. And in particular, we can essentially initialize some spin excitations at one end of the chain and then turn on this SSH structure of couplings and ask, what do the spin excitations do? And in the non-interacting case, they kind of oscillate from one edge to the other edge and back. That's this blue oscillation curve measuring the difference in spin polarization between the two edges. We start to turn on interactions, the oscillation actually gets suppressed. And as sort of a cartoon picture, or actually a physical picture for sort of why it gets suppressed, I find it useful to keep in mind that at least in the limit where these edges are kind of spectrally well separated from the bulk of my chain, I can basically think of this as a two-site Hubbard model, although the two sites are not directly connected. They're connected by the SSH chain. So there's some coupling between these two sites. There's some on-site interaction. The on-site interaction is zero. This coupling between the sites just gives me oscillations, essentially Rabi oscillations between the left and right edges, which I can visualize on some block sphere where up means all excitations are on the left, down means all excitations are on the right, and the transverse directions indicate the relative phase. So no on-site interaction, I expect Rabi oscillations. But if I turn on a strong on-site interaction, that actually gives rise in this two-site Hubbard model. There's a well-known phenomenon known as self-trapping, where the spin excitations kind of get stuck on one side. And that's what we saw with these oscillations going away. But there's also kind of a nice picture on this block sphere where I can think of it as I go from sort of processing about the x-axis, these Rabi oscillations, to sort of in the limit of strong on-site interactions, there are two fixed points of the dynamics that are instead tilted up and down along the z-axis. And so you can ask the question, can I actually verify that this is the right picture for thinking about these dynamics? Is it this self-trapping phenomenon that turns off the edge state oscillations? And the cute way that we can actually check this in the cavity is we can actually use the cavity as a non-local interferometer for accessing not just the sort of population information, but also the relative phase between the two sites. So this is an experiment where we initialize some spin excitations on the left edge. We then use the cavity to couple the left and right edges. And if you remember earlier in the talk, I showed you kind of Rabi oscillations between the left and right sides of the cavity. That's our non-local beam splitter. Then we turn on the SSH couplings, and then we close the interferometer again with this non-local cavity mediated coupling and read out the imbalance, the spin polarization of the edges. And then you can sort of map out not just the population dynamics, where there are these Rabi oscillations for no interactions, but also kind of the relative phase of the two edges, and see something that roughly seems to match these dynamics of precession about the fixed points. It's a little bit easier to see if one plots the derivative of the phase versus the initial imbalance, which is the z coordinate on the sphere, and one sees the characteristic behavior of these self-trapping dynamics. And I think the sort of fun thing here is we can use the cavity as this non-local interferometer to directly access this relative phase between the edges, and that so far is at the level of mean field dynamics of ensembles, but this is maybe a first exploration of this idea of using the non-local cavity-mediated coupling to access a non-local observable in the context of a topological phase. So with that, I think I'm out of time, and Marius is trying to get me to shut up. So I'll just briefly say, yeah, we're excited about the various directions this toolbox can go. And if you want to hear a little bit more about some recent theory on how these graph states we can build might connect to holographic duality, emergence of entanglement from geometry, there's a poster by my students that talks about graph states as a starting point for measurement-based preparation of states that have a sort of quantum critical structure of entanglement that connects to ADS-CFT duality. Okay, so that is just a teaser for the poster. And with that, I will just thank the team of people. Many of them are here. Some of them already showed you their labs, and I hope you'll ask them all the hard questions. So.
Thank you very much. Are there any questions?
John.
Suppose that I hate atoms, but I love optics.
Yeah.
It seems like some of these, like Chi2 kinds of things, one could think about exploring with like arrays of like Piplin crystals and Piplin cavities. Have you thought about like what one could do with that? Is that realistic? Is it hard?
I mean, so some of this, like, I talked about graph states, and actually like the place where these continuous variable graph states have been thought about in the past are in fact photonic systems. And so, yes, I think there are certainly photonic analogs of anything that we're doing with Gaussian states. So, why use atoms versus photons now depends what you want to do, right? For sensing, it will depend what you're trying to sense, and is it something that will, couple to light or couple to atoms? For more the sort of simulation directions, I think, I sort of flashed up some proposal about preparing certain structures of entanglement by starting from a graph state. And some of that actually could be explored in photonics, although I think it's kind of nice in atomic systems that like you can do something like prepare a certain state, measure out some nodes, you're left with an entangled state that sort of is long-lived, and you can do more with it. I think maybe somebody who works on photonics will argue against that. But it's another sort of example of where I think the atomic systems are kind of neat. I flashed up, and again, I referred you to the poster for sort of what does our next generation optical cavity look like. There we would like to, in fact, have single atoms and stronger coupling. And then you can still think about, do I maybe think about groups of those atoms as some sort of mesoscopic spin? And to lowest order, you could start by, let's say, making some multi-mode Gaussian entangled state. But you now have the ingredient of like atom number resolving detection, which is not so easy to do in photonics, counting 1, 2, 3, 4, 5 up through 10. And so there, for example, let's say for these Gaussian boson sampling experiments that try to show quantum supremacy, that's something that's explored in photonics, but it's kind of actually neat in atoms that you have the imaging as a nice way of doing atom number resolving detection. So I think there's strong synergies and then kind of maybe complementary capabilities of both. Yeah. Mm-hmm.
Then maybe in the interest of time, unless there's a, yes.
Okay. Yeah, so In full disclosure, so the first data I showed measuring this ZAC phase was, I think, 10 sites. Maybe we've done some version with 14, but for the edge states, there were only 2 dimers. The reason for that is this gap that gives you the oscillation frequency goes down exponentially. And I think maybe we could do it at 6 sites, but beyond that, it starts to get hard. So I would say it's so far kind of a proof of principle. But yeah, and that's the reason it's hard. It's not that it's hard for us to have more sites. Yeah, but the timescales do get difficult. So yeah. Mm-hmm.
Okay, then let's.
Okay, I'll chat afterwards. Yeah.
Yeah. Let's thank Monika again.
Okay.